Okay, so now if you guys talk or ask me questions, which you're allowed to do, you're consenting to have your voice on the video, aren't you? Yes, you are. Okay. Let's see what we got here. How the hell do I? Okay, copy, and then I'll go to my whiteboard, and for some strange reason, nothing happened. Okay, y'all see this, right? I hit copy, and then I hit Shift and Control V. Oh, dear Lord. Now I got to worry about this crap. Okay. All right. So we ready? All right. Okay. All right. Remind me to get the stragglers that came in late. Okay. So guys, what is the expression for the Kc for the following equilibrium? Now we're mindful of the fact that we take our products, the concentration of our products, and raise them to the power of their stoichiometric coefficients divided by the reactants, raised to the power of their stoichiometric coefficients. But there's a twist. We're not supposed to put solids and pure liquids in our equilibrium expression, are we? No, we're not. So that means I'm going to not include calcium oxide or calcium sulfite in my equilibrium expression because they're solids. So my equilibrium expression is going to, so Kc is going to equal to the SO2 concentration. Okay? All right, yeah. Yeah, I know you're saying to yourself, wow, that doesn't feel right, good doing it like that, but that's the way it's supposed to be done. So the answer to number one is B, right? Okay. Right. So going back to my, let me go ahead and let's go to number two. All right. Write the expression for the Kp. Now, if you guys recall, we since if you're dealing with gases, the pressure of a gas is going to be proportional to the molarity. Okay. If you recall, PV equals nRT. So that being the case, I can use the partial pressure of gases in lieu of concentrations, and I can work with it, and I can find the Kp the same way I found the Kc, right? So they say write the expression for Kp for the reaction below, and I know that I'm not going to include the bromine because it's a pure liquid, but I am going to include the NO because it's a gas, and NOBr because it's a gas. So the NO is a product. So I'm going to say the partial pressure. So I'm going to say the Kp is equal to the partial pressure of the NO squared divided by the partial pressure of the NOBr squared. Because the stoichiometric coefficients in both cases is 2 for the product and the reactant. Y'all see how easy that was? All right. And of course, if this was Kc, it would just be the concentration of NO squared divided by the concentration of NOBr squared, because it's always products over reactants. Okay. Uh, Number three, for which of the following reactions is the Kc equal to the Kp? Now we know that the Kp is equal to the Kc times RT raised to the delta N power, don't we? Okay, y'all remember that? Now, of course, the only time the Kc is the Kp is going to equal to the Kc is when the delta N is 0. Because guys, anything raised to the 0 power is equal to 1, right? So if I raise RT to the 0 power, it's going to be equal to 1. So then Kp is going to equal to Kc. Y'all see that, right? Okay, so Uh, so all we have to do is find out what delta N is and then figure out which one delta N is equal to 0. All right. So delta N is the moles of products, gases, minus the moles of reactant gases. So I'll give you an example. For A, delta N, I have 2 moles of gases in my product, right? And 1, 2, 3, 4 moles of gases in my reactant. So it's going to be 2 minus 4. So delta N would be a negative 2 for A, wouldn't it? Y'all see that? Okay. For B, delta N, I have 1, 2 moles of product gases, and I have 1, 2 moles of reactant gases. So delta N is 0. So you're saying, well, the answer is obviously B. But let's go ahead and take a look at C, D, and E. Okay, because we don't want to make the mistake that a lot of you guys made when you came to my office. I have for C delta N, let's see, I have 1, 2 moles of product gases and 1, 2, 3, 4 moles of reactant gases. So 2 minus 4 is negative 2 again. Okay. For D, calcium carbonate is a solid. Okay. So I have in calcium dioxide is a gas and calcium oxide is a solid. So I have 0 minus 1. So that's going to be minus 1. Okay. And then for E, bromine is a pure liquid. So I'm not going to include that at all. I have 1/2 minus 1. 1/2 minus 1 is a negative 1/2. Okay. All right. So, of course, you go with the one where delta N is equal to 0. All right. Y'all see how easy it was? Yes. Right. You never include solids in liquids in your equilibrium expression. Well, technically, solids, liquids, and solvents, but the solvent is going to be a liquid anyway. This is wet chemistry we're talking about here. So, yeah. Okay. Y'all with me? So if I give you a question like this on the exam, it's 3 points, right? No. Yes. Where did you get the, like, I was paying attention about where you got, where you were getting these numbers. Okay. All right. See, all I got to do is take the number of product moles. Okay. You see how I have that are gases. See how NH3 is a gas, right? See the stoichiometric coefficient right there is 2. So you take the product moles gases, the moles of products that are gases. In this case, it's going to be 2 minus the gas moles of reactants. See, I have a 1, 2, 3 right there and a 1 right there. So 3 and 1 is 4. So 2 minus 4 is negative 2. You follow me? But you only do it for the gases. Okay, so the 2 plus the 2 from N2 and 3H2 add those. Okay, it's going to be for the first one is going to be 2 minus 4 is equal to negative 2. Do you see where I got the 2 from? Yes. Do you see where I got the 4 from? 1, 2, 3, 4. So it's going to be minus 2. For the second one, B is going to be 1, 2 minus 2 is equal to 0. You see where I got the 2 from? Because 1 plus 1 is 2. And then I got the other 2. 1 plus 1 is 2. Okay. All right, you follow me? But like I was telling Layla, you don't include solids in liquids. So for example, D, I have, this is a solid. So I have 0 moles of product gases right here. And for D, I have 1 mole of product gases. So it's going to be 0 minus 1, which is negative 1. You follow me? Okay. All right. So moving right along. And huh? Delete it? Okay, I'll delete it. Nate wants me to delete it. Watch this. Oh. Huh? Okay. What the hell? I don't know why I end up saving that. Okay. All right. Okay, so far so good, right? Okay. So number 4, it says It says consider the formation of ozone by the following reaction. I have 3O2 yields 2O3. Calculate the Kp given that the Kc for this reaction is 2.5 times 10 to the negative 29. Okay. Now I want you guys to tell me what delta N is equal to. Negative what? Okay. Does everybody concur? Everybody concur? Ms. Harold, you see that, right? Because it's going to be 2 minus 3. So I know all I got to do is put Kp is equal to Kc times RT to the delta N power. Since delta N is minus 1, I'm going to say that, well, hey, Kp is equal to Kc. All right. Guys, anything you take it to the negative 1 power, you're basically putting it in the denominator, right? So I'm going to say Kp is equal to Kc times RT divided by RT. Now, if it was to the negative 2 power, it would still be in the denominator, but it would be squared, right? Okay, y'all with me? Okay, if it was to the negative 3 power, it'd still be in the denominator, but it'd be cubed. Okay, so, all right, we know that. So I'm going to say that Kp is equal to 2.5 times 10 to the negative 29. And I don't have to worry about units, okay? So I'm going to put my R down here, but I don't have to put the units down. I'm going to put the same thing for my temperature. I don't have to put Kelvin down because Kp is a unitless number. Okay, so let's see what we got here. So I would like everybody to do this. Give it a try. Okay, what did you guys get? Yeah, hey, I got 1.0 times 10 to the negative 30. All right, again, free points on an exam, right? Free points. Okay, so everybody's going to make an A, right? Yay, everybody's going to make A. Can I what? All right. La da 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 da. Chelsea, you play soccer? Okay, I'm sorry. You any good at it? What y'all having? Okay, all right. Okay, so number 5 says, of the following statements about the reaction quotient, now which of the following statements about the reaction quotient Q is false? Now, guys, as you recall, Q it has the same form as the K term. Okay, you still take the concentration of your products raised to the powers associated with their stoichiometric coefficients and divided by the concentration of the reactants raised to the powers associated with their stoichiometric coefficients. The only difference is when you find K, you use equilibrium concentrations. Q, you use initial concentrations. Okay, that's the only difference. All right. Now remember, if you guys recall, Q becomes K. Of course, at the beginning of the reaction, the concentrations are going to change. More often than not, you're not going to have any products around at all anyway. So the reactant concentration is going to decrease and the product concentration is going to increase until they get to equilibrium ratios, right? Okay. So the value of Q can be used to predict equilibrium concentrations. No, we can't use it to predict equilibrium concentrations. Okay. Uh, it has the same expression as Kc. Well, technically, it does have the same expression as Kc, but I don't know if they mean initial concentrations as well. Let's see. Let's see what we have right here. See, its value is calculated using non-equilibrium concentrations. Yeah, that's true too. So B is true, C is true. Okay. D, no, they asked which one is false. So I know B is true and C is true. D, if the Q is greater than the Kc, the reaction must move to equilibrium by forming more reactants. Yeah, that's true too, right? D, if Q is less than Kc, the reaction must move to equilibrium by forming more products. That's true too, isn't it? Okay. So the answer is A. The value of Q can be used to predict equilibrium concentrations, right? Okay, and let me erase this before Nate has a heart attack. Okay. Let's take care of that. And what I'm going to do this time, I'm going to go ahead and screen snip this bad boy. Okay, so let's take a look at this. All right, go to the whiteboard and okay, and let's see what we have right here. Now it says a 2.5 liter flask is filled with 0.25 moles of SO3. You have your hand up or you just stretching? You didn't get much sleep last night, did you? Hmm? Yeah. Okay. All right. So, yeah. So let's see. A 2.5 liter flask is filled with 0.25 moles of SO3, 0.20 moles of SO2, and 0.40 moles of O2, and are allowed to reach equilibrium. Assume the temperature of the mixture is chosen so that the Kc is 0.12. Okay. Predict the effect of the concentration of SO predict the effect on the concentration of SO3 as equilibrium is achieved by using Q, the reaction quotient. Okay, so guys, I made this problem. Well, I didn't actually. I took this off a test bank, but they made it harder than they needed to because they didn't give you the molarities. They gave you the moles and the volume. So you have to calculate the molarity, which is not that big of a deal. We can do that. 0.25 divided by 2.5 is equal to 0.25 divided by 2.5 is equal to 0.1, which is equal to the concentration of SO3. And then I'm going to take 0.20. Now, if I remember, I will 0.2 divided by 2.5, that's 0.8. 0.8 is equal to the SO2 concentration. And then let's see, for O2, I have 0.40 divided by 2.5, which is equal to zero point 0.4 divided by 2.5, and that's 1.6. 0.16 is equal to my O2 concentration. My initial O2 concentration, by the way. These are initial. Now I'm going to write the equilibrium expression, but this time I'm going to find Q. Well, I guess I'm writing the Q expression. So it's going to be the concentration of, since this is a reaction right here, is going to be the concentration of SO2 squared times the concentration of O2 divided by the concentration of SO3. All right, squared. That's going to equal Q, because these are non-equilibrium uh, concentrations. All right, so my SO2 concentration is 0.8. So I'm going to take 0.8, square that, and my O2 concentration is 0.16. All right, divided by my SO3 concentration, which is zero point 0.1 squared, right? Okay, so guys, to get this, all I'm going to do is I'm going to take zero point 0.8 times zero point 0.8 times 0.16 divided by zero point 0.1, and I'm going to divide it by zero point 0.1 again, right? Y'all see how I did that? So zero point 0.8 times zero point 0.8 times 0.16 divided by zero point 0.1 divided by zero point 0.1 again. And I ended up with, what the hell did I end up with? I think I did something wrong because I ended up with 1,024. 0.8 times zero point 0.8. Let me see. 0.4 times 2.5. Let's see. I think I may have done something wrong here. Okay, zero point 0.2 divided into 2.5. Let me see. Oh, yeah. This is wrong. This is supposed to be 0.08. Why y'all didn't tell me? 0.08. Let me do my SO3 again. 0.25 divided into 2.5 is equal to 0.1. Okay, so I'll make the requisite changes to that. 0.08. So now I'm going to take 0.08 times 0.08 times 0.16 divided by zero point 0.1 divided by zero point 0.1 again, and I get 0.1024. There's my 0.1024. Okay, so now we have found Q, haven't we? Now we're going to compare Q. Now is Q less than K or greater than K? It's less than K, right? Because Q is 0.1024 and K is 0.12. So it says predict the effect on the concentration of SO3 as equilibrium is achieved by using Q, the reaction quotient. So keeping in mind that Q is less than K. All right. So since Q is less than K, and remember, Q becomes K, right? All right. Since Q is less than K, the only way Q can become K is if my product concentration increases and my reactant concentration decreases. Y'all follow me? All right. So if my reactant concentration decreases, the only reactant I have is SO3, and that's what they want us to find out. That's what they're asking us about. So I'm going to go back to the one. So I know my SO3 concentration is going to decrease. So I'm going to find the one where Q is less than K and the SO3 concentration will decrease, and that's going to be V, isn't it? Okay, because Q is less than K. Now remember, all right, so anytime you have a fraction, okay, anytime you have a fraction, you're, let's see, I'm going to put 1/2 up here, all right? Now, I can increase this fraction by increasing the denominator or decreasing the, decreasing the denominator or increasing the numerator. Y'all follow me? Okay, so in this case, well, it takes two to tango. If I increase the numerator, I'm going to have to decrease the denominator. If I decrease the numerator, I'm going to have to increase the denominator. Okay, because it's products over reactants, right? If my product concentration increases, my reactant concentration is going to decrease. So the only way Q can become K is, since Q is smaller than K, the only way Q can become K is if my product concentrations increase and my reactant concentrations decrease. Y'all follow me? Okay. So since that means the SO3 concentration is going to have to decrease. Y'all with me? Okay. All right. So the answer, of course, like I said, is B. All right. Then now we get to the meat and potatoes. All right. We get to one where we actually have to do the ice chart, right? Okay. All right. So let's go ahead. I'm going to go ahead and snip this bad boy. Hopefully I don't screw up again. So go to my whiteboard, clear canvas. Why don't I? Pow. Okay, so let's see what we got here. Now, even though I'm supposed to be going over the study guide, let's see. Yeah, well, this one's yeah. Actually, this is not the meat and potatoes because you don't have to do an ice chart. You don't have to do an ice chart, do you? Yeah, I see that now. Okay, so if they give you initial concentrations and they ask you for equilibrium concentrations, that's when you have to use an ice chart. Okay, they only gave us equilibrium concentrations here, so this is just algebra. Okay, all right. In fact, this is beneath you guys, isn't it? So let's go ahead and they say for the nitrogen fixation reaction, 3 moles of hydrogen plus 1 mole of nitrogen yields 2 moles of ammonia. The Kc is going to be 6.0 times 10 to the negative 2 at 500 degrees Celsius. If 0.250 moles, if the concentration of H2 is 0.250 moles per liter and the concentration of NH3 is 0.050 moles per liter, what's the concentration of N2? All right, so it's just algebra, like I said. So I'm going to say Kc is equal to my H2 concentration cubed times my N2 concentration divided by my H. What the hell did I just? No, I did it backwards. Yeah, I'm sorry. Yeah. Well, I'm glad you guys pointed that out to me before I screwed it up. Wait, y'all did. I had to figure it out myself. Thanks, guys. I appreciate that. Yeah, you caught it. I'll give you that. Okay, so it's going to be my NH3 concentration squared divided by my H2 concentration cubed divided by my N2 concentration. So I know what the Kc is. It's Kc is 0.060. That's going to equal to my NH3 concentration squared, which is 0.050 squared, divided by my H2 concentration cubed, which is 0.250 cubed, divided by my N2 concentration, which is what they're asking us to find. So I'm going to put an X right there. Okay. All right. And all I got to do now is solve for X. So all I'm going to do is take 0.06 and take it. Well, I think I'll just go ahead and take 0.25 and cube that, multiplied by 0.06, and then divided by 0.05, and then divided by 0.05 again. Yeah, don't ever get old, guys. This sucks. Barely see the keys right in front of me. Okay, so I have 0.375 is equal to 1 over x. All right. And so I'll go ahead and get the reciprocal of 0.375. So x is equal to 1 divided by 0.375. There's going to be 2.6666666. So 2 2/3. So let's see how many significant digits is good to. It's good to 2. So x is going to be equal to 2.7. It's equal to x. Huh? Oh, I took the reciprocal because we're not trying to find 1 over x, we're trying to find x. So since 1 over x is equal to 0.375, the reciprocal of 0.375 is equal to x. So 1 divided by 0.375. Okay, all right. So the answer is B, huh? Okay, yeah, sure. Okay, yeah, I guess I should just do all of the algebra, write it all down. Okay, guys, I just thought you guys, well, okay, I'll just do it. So I'm going to say that 0.060 times 0.250 cubed divided by 0.050 squared is equal to 1 over x. Okay. Now, I could have just cross multiplied and gotten the x out of the denominator. That's probably what you guys would have done, right? Okay. Well, I guess I could have done that, but all right. Yeah. But y'all get it. Y'all see how I got to this point, right? Y'all don't? Yeah, y'all do. Okay, okay. So, of course, 0.06, well, 0.25 cubed is equal to, so I'm going to end up with 0.060 times 0.015625 all over 0.05 times 0.05, 0.0025 is equal to 1 over x. And then, of course, you end up with 0.375 when you do all of that is equal to 1 over x. Then I get the reciprocals. Then if you want to go ahead, 0.375x is equal to 1. So x is equal to 1 divided by 0.375. So x is equal to 2.7. Okay, y'all with me? Okay, so can I go to the other question now? The next question? Okay. Sweet. All right, so let's see if we have a nice or a rice problem. Yeah, we do. Okay, at 250 degrees Celsius, the equilibrium constant Kp for the reaction PCl5, 1 mole of PCl5 yields 1 mole of PCl3 plus Cl2. This is a nasty reaction, guys. Is 1.8. Sufficient PCl5 is put into a reaction vessel to give an initial pressure of 2.74 atmospheres. Okay, calculate the pressure of PCl5 after the system has reached equilibrium. So this is probably one of the easier ice chart problems because I don't think we have to use the quadratic, or do we? I don't know. Let me see. We about to find out. Okay, but notice that there's the stoichiometric coefficients are 1, right? All right, so let me. Okay. All right, and I need to decrease this in size just a tad bit more. All right. Okay, so, all right. PCl5 yields PCl3 plus Cl2. Now they're all gases. The only reason that matters is because we're using a Kp and not a Kc term. Okay, so I'm going to put an R right here for reaction. I'm going to put an I right here for initial, a C right here for change, and an E right here for equilibrium. So they told us that the partial pressure of PCl5 was 2.74. So I'm going to put 2.74. Okay, and since they didn't tell us the partial pressure of PCl3 or Cl2, of course, it's reasonable to assume that it's 0. Okay, all right. Now, all right. Now, what I'm supposed to do is find Q. Guys, it's obvious that Q is equal to 0, right? Q is equal to 0. Y'all see that, right? Because my product concentration is 0. All right. You guys, do you see that? Okay. All right. So that means I'm going to put a negative X right here. Okay. Y'all, since Q is less than the K, that means my reacting concentrations are going to decrease and my product concentrations are going to increase. So I'm going to put an X right there and an X right here. What if I had a stoichiometric coefficient of 2 right here? What would I put right here, guys? 2. Okay, all right. Don't forget that. So at equilibrium, all I got to do is add my initial plus my change. So I'm going to have 2.74 minus X. 0 plus X is X, and 0 plus X is X. All right. I'm going to write my KP expression. Okay, don't get lazy. Don't take shortcuts. Write the expression. You might make a mistake if you don't. I'm going to say KP is equal to my PCl3 partial pressure. Well, I'm supposed to say partial pressure. times my chlorine partial pressure divided by the partial pressure of PCl5. Again, if I had a stoichiometric coefficient of 2 right here, I would square this, wouldn't I? Y'all see that? Okay. All right, but I don't have that there, and I don't have to worry about it. So I'm going to go ahead and substitute terms in here. I don't know why I just put that there. Okay. I'm going to say I know my Kp is 1.80. I'm not on the top of my game today, am I? 1.8. But you didn't have to say it so quick. You didn't. So I'm going to say 1.80 is equal to x squared divided by 2.74 minus x, right? Snap. This is looking like a second order polynomial, isn't it? Isn't it? We get to solve a quadratic equation, don't we? Yeah, so I'm going to go ahead and multiply both sides by 2.74 minus x. I'm going to say 1.80 times 2.74 minus x is equal to x squared. So I'm going to say 2.74 times 1.8 is equal to 4.932 minus 1.80x is equal to x squared. Now, do you want me to take my x squared to the left or take those two variables on the left to the right? Oh, yeah. All right. Well, there's nothing wrong with a negative a term. Negative x squared minus, I'm going to go ahead and rearrange this, minus 1.80x plus 4.932. I encourage you guys to do it that way too, so you don't confuse your B term and your C term. Okay, I went ahead and I put my B term in front of my C term. So my B term is right here, and my C term is right there. I put my B term right here, my C term right there. So, yes. Okay, remember you can take the approximation if you take your K term, you multiply it by 100. If that's less than your initial reactant concentration, then you can get rid of this minus x. You can take the approximation. But if I multiply 180, well, 1.8 times 100, I'm going to get 180, right? 180 is greater than 2.74. Yes. Well, yeah, you'd multiply, yeah. If your K term times 100 is less than your initial reactant pressure, then you can take the approximation. Okay, that's not the case. So, of course, what is A, class? Negative 1. What's B? Negative 1.80. All right, you guys not going to let that slip you up. Okay, and C is what? Okay, so you guys going to use those fancy calculators of yours, and you're going to tell me what x is equal to. Now, recall that you'll probably have a negative term and a positive term, and since my PCl3 concentration is x, and so is my Cl2 concentration, I can't have a negative concentration. I'm going to go ahead and dismiss that negative value that I get for x. Let me go ahead and get it in. Okay, because your X is equal to your Cl2 concentration and your PCl3 concentration. And you can't have a negative concentration now, can you? Yeah, negative pressure. You can't have a negative pressure. All right, my bad. So I came up with an X equaling 1.496247. And let's see. And of course, I ended up with an X equaling a negative 3.296. All right. So which one of those am I going to get rid of? The negative one, right? Okay. Did you guys get the same thing? Y'all did. Just solve it. Okay. Now, if you want to solve the quadratic equation and waste all your time, you can. Don't mind. I don't mind one bit. You'll probably won't do well on the exam, but hey, yeah. Or you could come to my office and we could write the program. I put it in your calculator. Or if you have a calculator like I do, a non-graphic scientific, it's already built in. Yeah. Okay. All right. So Okay, so I got 1.46, and I don't know how many significant digits this thing is good to. It's good to 3. 1.46 is X. So notice they didn't ask us to find X, which is the PCl3 concentration and Cl2 concentration. They asked us to find the equilibrium PCl5 concentration. So I need to find 2.74 minus X. Okay, since X is equal to 1.46, I'm going to put 2.74 minus 1.46, and I end up with 2.74. Oh, I screwed up again? Okay, well, yeah, maybe I screwed up again. All right, I'll take your word for it. 1.496. So we're going to round this up to 1.50, right? Yeah, I'm not on the top of my game today, guys. I apologize. I'll try not to screw up again. 0.74 minus 1.5. That's going to be 1.24. Yay. Okay, so let's see what we got here for answers. So we're going to find a partial pressure. So my PCl5 partial pressure is 1.24. Y'all see how easy it was? Okay, so guys, all right, you're going to have two problems like that on the test. One where you get to take the approximation. Of course, it's going to be a weak acid problem. Well, actually, you're going to have three problems like this. So 3 problems where you have to use an ice chart. One of them, you're not going to be able to use the approximation, right? Okay, guys, you have no excuse for not getting this right. Okay, yes. I don't know. I haven't made the test out. Who the hell called me? I haven't made the test out yet. Okay, number 9 says consider the following reactions and their associated equilibrium constants. A plus 2B yields C. Okay, and we're going to call that K1. The K for that reaction, we're going to call it K1. And then another one is going to be C yields D plus E. We're going to call that K2. Now, of course, if you add those reactions together, you're going to get the reaction at the bottom. A plus 2B yields D plus E, right? Okay, so we're calling the K for that reaction at the bottom KC. So KC, how would you get KC using the K's, K1 and K2? Yeah, you just multiply them together, right? Okay, so the answer to that would be what? Yeah, D. Okay, shit, how many more of these do we got? 2. Okay, so do I have enough time to do them? Okay, well, let's see. For the following reaction at equilibrium, which one of the changes below would cause the equilibrium to shift to the left? Okay, now we know that this is an endothermic reaction because my enthalpy change is a positive 30 kilojoules. Had it been a negative 30, that means it would have been exothermic. The fact is a positive 30 means it's endothermic, right? Okay, so anytime you have an endothermic reaction, heat is a reactant, right? If it's exothermic, heat is a product. Y'all with me? Okay, all right. So we're going to take these one at a time. Remember, we're trying to shift it to the left. So shift it to the side with the towards reactants. Okay, if I increase the container volume, okay, if you guys recall Boyle's law, volume and pressure are inversely proportional. So if I increase the volume, I'm decreasing the pressure, right? So according to Le-Chatelier's principle, it's going to try to counteract that change. So if I decrease the pressure, my system is going to try to increase the pressure. The only way it's going to increase the pressure is if it's going to shift it to the side where there are more moles of gases. Okay, so you go ahead and you find delta N. Okay, notice that I have, if delta N is, well, you don't have to find delta N. I have more moles of product gases, right? I have 3 on the right and I have 2 on the left. So it's going to shift it, in order to decrease the pressure, it's going to shift it to the product side. It's going to shift it to the side where more moles of gases are on. Y'all follow me? To counteract what I did. So Le-Chatelier's principle says the system is going to try to counteract whatever I do or whatever you do to it. Yeah, well, that's how you increase the pressure. Okay, it's going to decide with more moles of gases. Okay, what if I remove some NO? NO is a product in it. If I remove product, it's going to try to create more product. So it's going to shift to the right. So it's not that. What if I remove some BR2? Same thing. It's a product, BR2. So it's going to shift. If I remove some BR2, it's going to try to make more BR2. So it's going to shift to the side where there's to the right, where the BR2 is on. What if I add more NOBR? If I add, which is the reactant, it's going to shift to the right because it's going to try to get rid of that reactant. The only way you can get rid of that reactant is to form products at the expense of my reactant. If I decrease the temperature, remember this is an endothermic reaction. Temperature is a reactant. So if I decrease the temperature, I'm taking heat. Well, heat is a reactant since it's endothermic. I'm taking heat out of the system, right? If I decrease the temperature. So it's going to try to counteract that by shifting it to the left. Okay. All right, so the answer is E, and let me see. Number 11, in which of these gas phase equilibria is the yield of products increased by increasing the total pressure of the reaction mixture? Okay, so if you increase the pressure, you are part of the surroundings. My system is going to try to counteract that by decreasing the pressure. It's going to decrease the pressure, all right? So it's going to shift it to the side with less moles of gases. So all I have to do, find the one where I have less moles of product gases. Okay, so right here, A, I have they're equal is 2 and 2. 2 moles of product gas and 2 moles of reactant gases. For B, I have more moles of reactants. For C, I have more moles of products. Oh, okay, yeah, we're done. Anyway, the answer was what? The answer was B. Yeah, okay. All right. Okay, you can come in next one. Okay, so let me go ahead and stop recording.